Dear students, I'm Ajman and today I'll be explaining the further mathematics paper 1 solution. So our first question is a roots of polynomial question. Over here we are given a quartic equation. So over here we're given a quartic equation and then we are asked to use this substitution to show that y satisfies this equation. So basically this is transforming this quartic equation to another quartic equation. So how do we do that? We have y equals to x cube. So we find out what is x equals to, then we can substitute it. So x is equals to y to the power 1/3. Then we substitute this x into this equation, so we get y to the power 4 by 3 plus 3 by 3 is 1, so y minus 2 equals to 0. Then since this has a weird fractional power, we want to make this a subject and then cube everything to remove it. So y to the power 4 by 3 is equals to 2 minus y, and then we cube both sides and use binomial to expand, and then we come to this step. And then we simply simplify, and when we get this, and then we just simply rearrange to get the final equation. So pretty straightforward. Our next question is to find the equation, to find the exact value of alpha cube, beta cube, x cube. So over here, we have to find, basically they want us to find the solutions of this equation and find the values of the x's. So all the roots. So it will have 4 roots. So those will be the alpha, beta, gamma. So let those roots will be alpha, beta, gamma, and delta. So it's a quartic, there will be 4 equations, and then they want the cube of those. So since while transforming this equation to this equation, we cube the x. So this equation solution should be the alpha cube, beta cube, and gamma cube, and delta cubes. So we simply need to solve this equation. So solve as in, like, we can just simply use the Vieta's formula to find the sum. Since they don't want us to find the actual alphas and betas, they just want us to sum, we can use Vieta's formula. So over here we have so over here they use a Vieta's formula. So the sum of the roots of y, which is minus b by a, in other words, so it's simply the second variable. So coefficient of this value is 1 and the coefficient of this value is 1 again. So 1 by 1, so minus, and then minus in the front, so it becomes minus 1. So yeah, that's it. Our next question asks us to find the alpha to the power 6. So since this is the, so that would be, since this is the sum of the y's, this would be the sum of the, if this is the sum of the y's, then this should be the sum of the squares of y's. So basically, since y is x cube, squaring y, we get x to the power 6, and those roots we want. So now we will use that. So again, same thing, Vieta's formula, but this time it's for the square ones. So we'll use this formula. So we already have the sum of the y's, the roots of y, so which is minus 1. So square that, and then this this again. So this is the pair formulas. So y1. So each of the coefficients multiplied. So it's like alpha, beta, beta, gamma, and then beta, delta. Also all these possible pairs, and then sum them. Also they're cubed, right? Since it's y and y is x cube. So yeah, that's it. So the formula for that is so positive c by a. So what's c here? Let us see. C is minus 6, and what's a is again 1. So minus 6 by 1. So minus 6 by 1 is simply minus 6, and multiply that by minus 2, we get plus 12. Plus 12 plus 1 is 13. So yeah, that's it. Next question asks us to find the exact value of alpha cube minus 2 whole square. So this one again, it's simply, we can since it wants basically the all the sum of all the roots. So basically alpha cube minus 2 square plus beta cube minus 2 whole square plus gamma cube. So all these 4, basically these 4 sums. So how do we do this? We first open the brackets. So we first simplify this. Since we cannot find it in this form, we just simplify and turn this into a problem we already solved. We already know the y, sum of y square, and then sum of the y, and then we can square sum of the y's we already know. So we turn this problem into that problem. So how do we do this? We simply expand. So we get y square minus 4y plus 4, and then we simply open the bracket. So and separate out the sum formula. So sum for this, sum for this, sum for this, and then we simply replace. So this is sum of y square, so which is 13, and the sum of y, which is minus 1. So minus 1 into 4 is 4, and the sum of the 4. So we have since there are 4 variables, so is basically 4 into 4, so that's 16. So yeah, that's a 13 plus 4 plus 16, and we get 33. In these questions, we have two lines, L1, which is parallel to the vector, this vector, and where a is a constant and it passes through the point. So this point, so it passes through this point and it's parallel to this vector. So basically, this is basically the direction vector, and this is the basically the one of the points. And L2, another line that's parallel to, again, same kind of stuff. So this is the direction vector, and this is one of the points. So to create the line equation, we simply put the point here. So this is the line L1. So it's basically the direction vector over here, a minus 2 1, same as this, and then the one of the points, so 0. So we can put this as a starting point, and then a parameter. And for the second line, same thing again. So we take one of the points, so this point, put it here. So this will be the starting point, and this will be the direction vector. So we can put this here. So yeah, so it's pretty straightforward. Then we simply, since it is shown, it is given that L1 and L2 intersect, so that means they're equal at one point, right? So these are two lines and they meet at one point. So both of the x, y, z coordinates should be equal over here, right, for both of these equations. So what do we do using this information? We simply equate them. So 0 plus a lambda is equals to minus 5 plus let's just put minus a mu. So we're just equating this line with this line, and same thing we will do for two more. So another one here equals to this. So that way we'll have two equations. So over here we use a second line for this. So minus 5 minus 2 lambda plus minus 2. So it started with the second line. So this line. So equating the y component, and then it simplified this. Basically, this is a simplified form of the equation for the y component, and then it did for the z component. You can do for any two components, and then you'll find two equations, and then you solve these two equations using Samdani's equation. So basically just elimination or substitution, and then we will have the mu and lambda values, and then we use that for the first equation, because the first equation had the a values, right? It was an unknown, that's why we used the second two equations. So then since we have the parameters, we can use them on x, and then using that fact we will get the value of a. So pretty straightforward. To summarize again, we have to form the equation with the direction vector and a point. So using that for both of the lines, we create two equations, and then since we need to find a, we use the second and third equations, because we know that the x and x, y and z components are equal, so we can just simply equate them, and we have two equations, one for y and another for z. So over here that's done, and then we solve and find the hyperparameters mu and lambda, and then we use this in the first equation. So over here again, for the x components, we equate the first line. So a lambda is equals to minus 5 minus a mu, and then we solve this to get the value of a. So over here we already found lambda and mu, so it's just one unknown a. So yeah, pretty straightforward. Next one is find a Cartesian equation of the plane containing L1 and L2. So basically it's a plane and it contains the two lines, L1 and L2. So let's say these are these 2 points, and both of them are on this line wholly. So it's like wholly, even that intersection point. So these two lines are in this point. So basically what we can do is we need to we can use it asks for the Cartesian equation, right? So how is the Cartesian equation? It is a plane with the direction vector being this perpendicular to the line, to the plane. So how do we get that? Since both of these lines are in the plane, we can simply find the cross product. So if we get the cross product, we'll get the direction vector. So that's what we do here. We find the cross product of these two lines. So d1 and d2 are the direction vectors. So over here we find the cross product and get this. So we have minus 7x plus 4y plus z, and then we simply can use one of the points. So over here we have 0 5 1, right? So we can substitute this point into this. So 0 5 1, so minus 7 into 0 is 0, 4 into 5 is 20, plus z is 1, so equals to 21. So equals this. By the way, this will be the constant, the d. So we are trying to find out the d over here. So 20 plus 1 is 21. So yeah, that's it. This is another method. Both method works. Same thing. So this will be the final answer. So over here we are given a set that the perpendicular distance between L1 and L2 is 35. This number 35 by root 3. So find the value of A. So we are given that the perpendicular distance. So basically we have the two lines again, L1 and L2, and the perpendicular distance, which is also the shortest distance, is let's say it's somewhere over here, and is this value. All right. So and then we want to find the value of A using this information. So let us. So what do? We can find we don't know where this point is, right? Where the two lines are perpendicular exactly. But what we can do is we can find the direction, right? The direction vector of the perpendicular distance. So over here, if this is the one vector and this is another vector, so this is one vector and this is another. Let this be L1 and L2. And if this line, the shortest distance, is perpendicular to both of them, that would mean we can again use the cross product to find out the direction of this at least. So this is what we do. We find the direction. We use the cross product to find the direction. So this is the direction vector n. And then we can also find 2 points. We know 2 points, right? A, B. So basically, the 2 points are given. This point and this one. We can see this again here. So we know these 2 points. So we can create a line like this. So let's say this is A and this is B. So let's create a line like this. So this is the we can find out this vector also. So we subtract. So over here, this is what we did. We subtracted R2 and R1 and we got this direction vector. So with its length also. So the modulus of this will be the length of this vector. So and then we project this vector onto this vector. So that way we can find out the length of this. So it will become the length of this. But we have to make sure this is the unit vector n. So basically we found out the direction of the vector that's perpendicular to both, and then we'll also divide by the modulus. That's why we found the modulus here. We'll find the modulus n. So that way you can only get the direction vector, unit vector in this direction. And then we project the vector AB into this line. So how do we do that? We simply do a dot product. So AB dot product with this. So AB. So what we do, we are in the end projecting this vector AB onto this line, and then we'll get the perpendicular distance between both of the lines. So that is exactly what we do. This is the calculation over here. So R2 minus R1, so that is this vector AB into n. So we're multiplying this and we get this, and then we are dividing with the modulus. So because we want to make sure n by n modulus of n, that way we are projecting with the direction vector, or else this vector's length and the normal vector's length, this has no relationship with the actual perpendicular distance, right? That's why we need the unit vector, else we will get something that crosses this line if you just simply multiply it with n. So we divide by the modulus, and then that's what we did here. So over here we have R2 minus R1 into n, so which is this, divided by the modulus, which is this, and we know this is equals to this, and then we solve this equation simply and we find the two values of A. This is another very straightforward question. Over here we are given an equation for the sum of the series formula for UR, so which is this till n, and they want us to find, so we are given till n, so from 1 to n, and they're asking us from n plus 1, so one number after this, till 3n. That's what they're asking us. So how do we do this again? It's very straightforward. So we just take the sum of sum till n, so from all the sums from here to here, and then simply subtract this part. So in other words, S3n minus S3n minus Sn. So that's what we do here. So we simply input 3 into the equation to get this. So this is S3n and this is Sn, and then we subtract and we finally get this. So yeah, that's it. Second question, we had asked us to find out the value of the UR. So we know the series formula, but they're asking us for the sequence formula. So how do we do that? We simply take the last term and subtract it with the previous term, but we do it algebraically, so we know the difference. So basically the difference will be the UR. So basically, so that will be, we have SR here, and then we subtract the SR minus 1 and then simply solve this and we get this. So that is the UR. So the first one is a straightforward induction question. Over here we are given this equation 3 to the power 2n plus 7, and we to show that it's divisible over 8 for all non-negative integers. So we have to be careful here because it asks for non-negative integers. A lot of people show that it's true for n equals to greater than equals to 1, but it said non-negative, so it has to be n greater than equals to 0. All right, so we first, our base case, we should start with 0. So that was a mistake. People used 1 instead. So that's that. So they have ended up proving for this instead of this. So over here we start with base case n equals to 0, and then we see 0 to 3 to the power 0 plus 7, so that's 8. So it is divisible. So base case is divisible, and now we assume it's true for n equals to k. So and then we show that it's true for the next integer. So yeah, so let us do that. So let me just rewrite it. So 3 to the power, we are showing for this n is equals to k plus 1. So k plus 1 plus 7. So that's 3 to the power 2k plus 2 plus 7. We can take the 2 forward, right? So we can turn this into 9 into 3 to the power 2k plus 7. It's approaching the result we already know. We already know this 3 to the power 2k plus 7. So we're not quite exactly there. What we can do is we can separate this out. So we can turn this into 8 into 3 to the power 2k plus 3 to the power 2k plus 7. So I just broke this term a bit, so into these two terms. And then we know, of course, obviously this is divisible by 8, right? Because it has an 8 as a factor. And from our previous step, we assume this is true. So we know this is also divisible by 8. So basically, and so since this is divisible and this is also divisible, the sum should be also be divisible. So yeah, that's how we can prove it. And then since we did it for base case with n equals to 0, it is proven for all n greater than equals to 0. You can also do this way. It has an 8m, so it's just saying that any random integer into 8. This is true. So over here they replace this part with 8m. So and then take 8's common. So this must be divisible of both of them. So our next question looks a bit complicated, but it's actually also not that hard. So we have to prove that differentiation of this is equals to this for all positive integers then. So since positive integers, we have to start with n equals to 1. So simply without thinking much, just try the base case. So dn is equals to 1 and n is equals to 1. So over here, that's what we did. So we took the derivative of x, e to the power of x, and we got this. And then we took e to the power of x common to simplify this further, to make it more like this form. So yeah, and is this true? Yeah, let's see. N is equals to 1, and then yeah, it's true. So the base case is proved, and then we assume it's true for n equals to k. So the derivative of, so the kth derivative is x plus k e to the power of x. Just rewriting this, and then we try for n plus 1. So n is a k plus 1. So n equals to k plus 1. So over here we take the this is what we need to prove. We need to prove that it's also true for this, given this true for this. So over here we did the k derivative k to the k to the first derivative, sorry, k plus 1, and that number derivative. So over here, and then we take since differentiation is like this, since if it's like d cube by dx cube, it simply means you could rewrite it this as dx as d square by dx square, or we could even make this like this, dx square by dx. Obviously the function is over here, so f of x. So we simply did that. We took one of the d by dx's out, and we have this. Since we have already proven, we're already assuming that is true for d to the kth power. So we have this, and then we use this x plus k. Since we're assuming this, we can use this over here. So it goes to becomes like this, and then we differentiate. So after we differentiate, again just simply using the product rule here. So x plus k over here, we are taking u as e to the power of x. So simply like that, using the product rule here, and then we simplify. We take common. We take e to the power of x common, and then we can see x plus k plus 1. And since we are proving it for k plus 1, we take k plus 1 and put them together, and it simply again just like the formula, x plus k plus 1 e to the power of x. So the formula works. So hence it's true for all positive integers. So in this question, we have a curve y equals to this, and then it asks us to find the equation of the asymptotes of c. So simply first asymptote is pretty straightforward. We just said x minus 1 equals to 0, the denominator equals to 0, and x is equals to 1. So that's the vertical asymptote. And for the oblique asymptote, since the power is higher, we have an oblique asymptote, so we simply use polynomial long division. So this is what we did. We divided the numerator by the denominator, and then this is our remainder and this is our quotient. So we simply put this here, x plus 2, and then the remainder over this. So and then when x goes to positive or negative infinity, this term becomes 0, right? So yeah, here shown it becomes 0. So we are left with x plus 2. That means this is the oblique asymptote. So our next question, find the turning points of the point C. So this is very easy. We just simply differentiate and equate it to 0. So yeah, that's what they did. We differentiated using the quotient rule, equated to 0. So this term equals to 0. So this goes away. So over here, and then we simply use middle term breaking to get the two points, 3 and 1. So 3 and minus 1, and then so 3 minus 1, and then we simply input this into the original equation, into this, and then we get 7 and minus 1. So yeah, this would be the turning point. So just simply differentiate and equate it to 0. Next question, to find the coordinates of any intersection with the coordinate axis. Again, simple question. So we just set x equals to 0. So we set x equals to 0 in this equation, and what do we get? We get 2 by minus 1. So 2 minus 2. So y-intercept is minus 2. And then for the x-intercept, we set y equals to 0. So y equals to 0. So x minus 1 into 0 is 0. So x square plus x plus 2. And then when we solve this quadratic, we get, this is not solvable. So we can simply see by b square minus 4ac, which is 1 square minus 4a is 1. So 1 into this is 2, by the way. So 1 into 2. So 1 minus 8. So this is great. This is less than 0. So hence the discriminant is negative. Thus it means there is no solution. So there is no x-intercept. So now we can sketch the graph. So what was our asymptote? So we had asymptotes x equals to 1 and y equals to x plus 2. So over here we have an y equals to x plus 2. So this is the asymptote line, and then x equals to 1. And then we know that it doesn't connect with the x-axis, and we also know that the maximum and minimum points. So the maximum points and the minimum point and the maximum points over here, and we also know the x-intercept. So we simply draw it like this, because we can also see that since if we draw these 2 points, we already know that it will be like this. It has to be the maximum, and this has to be the minimum. This has to be the minimum points, or the curve has to go like this, and this is the maximum point, the curve has to go like this, and we simply connect this line also. So yeah, that's it. So over here we have a polar coordinate question. So over here we have two curves C1 and C2 with these equations, and we need to find the polar coordinates at the point of intersection of these two curves. So what do we simply equate them? So root 2 is equals to 2 root of sine theta, and then we get sine theta equals to 1 and 2, because 1 and 2. Sine theta is equals to half. So let me calculate that. So root 2 by 2 is equals to root sine theta, and then we simply square both sides. So we get square. So 2 by 4 is half. So half equals to sine theta. So using the quadrants, so we have this quadrant is like 0 to pi, 0 to pi. This is still pi, right? So we have to consider this both of these quadrants to see the intersection, because they're going to intersect anywhere here. So the first one is sine theta equals to half, right? So using the calculator, we can find the base angle, which is pi by 6. And then since it's sine, sine is positive here and here, we'll also have an answer in this quadrant, which will be 5 pi by 6. So 5 pi by 6, and then we simply we don't even have to put in the equation, because one of the equations simply root 2. So root 2 will be the radius. So root 2, and then these 2 points. So this will be the two intersections. So firstly, there with the equation root 2, it's simply the radius is root 2 everywhere, right? So it's simply a circle. And for the 2 sine theta, root sine theta, first let's think of sine theta. So sine theta's graph is simply this, a circle, right? And then since we're rooting it, and since the values are less than 1 over here, so they will increase in every point, right? Except over here, where again the root of 1 is simply 1 again, right? So it will become 1. So over here we can see that it increases a lot here because small roots, since it's less than 1, they will always increase when you root them, and the smaller numbers increases a bit more. So over here it increases more, and then it starts it decreases, it increases less and less until it's just 1, and then we simply multiply this by 2, so it's a bit bigger. So over here, that's why we have this curve like this, and we can see the 2 intercepts over here, so which we got from the previous question. So okay, so now find the exact value of the area enclosed by C1, C2, and the half line theta equals to 0. So half line theta equals to 0. So what are the lines? So enclosed by these two, and y theta equals to 0. So the angle is this. So this line theta, so C1 and C2. So right, so this has to be this area. So this is the area we'll find. So first, let's find out the area of. So first, the area equation is simply half r square theta. So and then we subtract this equation. So basically, if you find the area, we'll get area from here to here to here, and then we subtract this out. So this part out. So that's what we do here. We find the area of the root 2, and we subtract out the sine theta. So we're left with this area only. So yeah, and we take from 0 to pi by 6 because it starts from 0, the angle over here, since we say the half line theta equals to 0, and ends over here. So yeah, and then we subtract and we get this. So over here we need to find out the matrix M, which represents the sequence of 2 transformations, so which are given by 30-degree anti-clockwise about the origin, and one-way stretch in the y direction. So basically the first one, let's say a point is here, it will take us 30-degree anti-clockwise, so to this transformation, and then a stretch in the y direction. So it will basically, if you have a, let's say, square like this, it will stretch in the y direction only, so it will become like this. So that's what we do here. First we find out the, so using the anti-clockwise rotation matrix, which is this, we simply input the value 30 and we get this. And for the stretch, since we're not stretching x, we're only stretching y, we just use this matrix where we have a value in the y. So this will stretch any image we have. So we simply multiply them and we get this. So next question, unit square in the xy plane is transformed by M into a parallelogram of area 2k unit square. Show that k is equals to half. So it's a unit square, right? And then we are using this, multiplying this with this M, and then we get half. Sorry, not half, 2k square. So basically, to do this, since it's unit square, we can simply find what matters is the area of this M. So we can simply, how do we do that? Of this transformation, we found out the determinant of the transformation, which will give us the area, which will tell us how when it stretches the area, basically it will give us the area of the transformation. So which is what we do, we get the determinant. So simply using the determinant formula, and then we equate it to 2k square. So this determinant is k. So we first found the determinant k, and then we equate it to 2k square, and then we get the value of k. Okay, next question asks us, find matrix N is such that Mn is equals to 2 1 2 1. All right, find N. So so this is Mn, right? So if this is Mn 2 1 2 1 1, we multiply the inverse of M on both sides to get N. So that's what we do. We find out M is this, we find out the inverse of M, which is this, multiply it with this, and we get N. So in this question, we have to so find the equation of the invariant line through the origin. So of the transformation xy plane represented by Mn. So basically, an invariant line is such that, like, when we align like this, so it goes to the origin, so y equals to mx. So such that when we use the transformation Mn, it takes any transformation on any point takes the point back to this line again. So somewhere here could even be the same point. If we multiply Mn with this, it will take the same point to here. Other points could go other way, but if the point is in this line, it will go back to this line. So how do we do this? Firstly, we gotta recognize that the equation of this line is y equals to mx, since it's a straight line through the origin. Then since it's y equals to mx, and if we let x be the x coordinate, then the y coordinate must be mx. So this is our first point. The point we're gonna transform is, let it be x and mx. So let's do that. We multiply the matrix Mn with x mx, and we get this. So this is our transform point. So if this was the point, this is our transform point. It's in the same line will be x prime, let it be x prime and y prime. So the x prime is equals to simply 2 into x plus mx. So simply matrix multiplication. This will become, so this matrix multiplication would become 2x plus mx, again 2x plus mx, and they are the x prime this one and y prime this one. Simply it rewrote this again here. So when we took x common to make it simpler, we'll see how it helps later. So for the invariant line, again since it's the same line, this also follows, right? Y equals to mx follows. So since the new points are y prime, we can simply write it like this. So using it, we can substitute the x prime and y prime into this equation. So that's what we do. We substitute them. So y prime becomes this and x prime becomes this, so multiply with m. So now we see, let us take everything to the same side and open the bracket. So let us do this. So 2x plus mx minus 2mx minus m square x. We can see the x is in every single term, so we can just take that common. So x 2 plus m minus 2m minus m square. We can see it's a quadratic. We can simply using middle term breaking brackets. It's already broken, so we can just take common. So first thing we take common is 1 from this side and minus 2 from minus m from here. So 1 minus m, will they be equal? So if it's m plus 2, we come because this becomes m. So yeah, they're equal. So this becomes 2 plus m. So yeah, this is factorized. And obviously, since we took that this part left, this was equals to 0. This is equals to 0. Equals to 0, 0. So this becomes x into m minus m 2 plus m equals to 0. So we can get the m values from this. M is equals to 1 and m is equals to minus 2. So what would our equation be? Y is equals to x. So we simply input the m value. So y is equals to mx. So m is 1. So that means it's simply x. And other is minus 2. So y equals to minus 2x. So these are the two cases. Now we have to check, like, since we can also have solutions like this, right? A vertical line through y. So this line, we could have this could also be an invariant line. So like a point from here could go also from here to here, right? Now why this line doesn't count, this line cannot be considered in this type of equation, y equals to mx, because if we set m to 0, then y is equals to 0. So it is this line. But if we cannot represent this x equals to 0 using this equation, so what do? We do a separate check for that. So check the vertical line x equals to 0. How do we do that? We can simply let let us see the nature of the line. So x is always 0 and y can be any value. So the points equation, points vector can be written as 0 y. So that's why we multiplied with this. So 2 1 into 0 1. Now we see that the x value is y. That means it can change. If you multiply, it will come. It will transform to like this, basically. So if it was 0, then we would know, okay, it's in the same line, but the transformation takes it to somewhere else. So x equals to 0 is not one of the solutions. So using this test, we can find this. So yeah, that's it. Finally, last question. Over here we have we are given this this algebraic expression, and we need to expand and simplify. And so this is pretty straightforward. Just a one more question. So first we use binomial to expand r plus 1. So that's r to the power 4 plus 4r cubed plus, so 4c2, which is 4 into 3 by 2, which is 6. So 6r square plus, it's symmetric, so 4r plus 1, and then minus r to the power 4. So they cut each other out and we are left with this. Yeah, so that's it. Very straightforward. Next question is use the method of differences together with standard results, this and this, to show that r cube equals to this. So we need to use this result to prove that r cube is equals to this. So proving the r cube formula in this way. So first let us use the method of difference. So let's study it a bit. So okay, so from here let us convert this problem to this problem. So we can see that this sum is equals to this. We got it from here, right? We just convert this into this and then distributed the summation formula. So now we can use all the r square and r formula. So which is what we did here. r square and r formula, and we have this. And this part, as for this part, let us try this, the method of differences. So summation of r plus 1 to the power 4 minus r to the power 4. Let us try the value of 1. All right, so when it is 1, it's r plus 1 is 1 to the power 4. Sorry, 1 plus 1 is 2, 2 to the power 4 is 16 minus 1, so that's 15. Okay, let's keep this separate for now. And then next term 2, so 2 plus 1 is 3, 3 to the power 4, 3 to the power 4 is 81. 81 is it 9? Yeah, 81. And then minus r, right? So r is now 2, so 2 to the power 4 is 16. Over here we can already notice a pattern, the 16 and this cuts out. Let us see if it keeps on going. So let us try r equals to 3 now. So at 3 we have r plus 1 is 4. 4 for the 16, 16 into 16, that should be 256. Let's check. 16, 16. It's 6 is a 36, left 3, see, left 3, 6, 9, 16, 6, 15, left 1, yeah, 256. So 256 minus our r is equal to 3, so 3 to the power 4 is 81. Again, this one cuts out. So we can see a pattern over here. So the method of difference shows that the last number which shall be n, right? So n plus 1 to the power 4 will remain. Since every term, this term is remaining, so 256 will be cut off again. But then we keep on going till we reach n plus 1 to the power 4. N to the power 4 will cut whatever is here. So it will, the only thing that will remain is this part and this. So n plus 1 minus n plus 1 to the power 4 minus 1. So that's how we got this result over here. So these two sides are equal. Now it's algebraic manipulation. So we make this the subject, since we're trying to find this out. So make this how we get everything to the same side. So n plus 1 minus 1. Also, oh yeah, 6 gets cuts off. 2 and 4, so this becomes 2. So this is n plus 1 minus oh yeah, so this part, yeah, so this part is this, and this one is this, and n minus 1. So this is basically minus 1 and n getting together. So n comes here and it becomes minus n minus 1, and take minus 1 common, n plus 1. So again, since all the terms are here, then we can see that n plus 1 is in every single term. So we just take it common, since we can see in the final form n plus 1 has a square on top of it. So we should take common whenever we can. So and we should take, since it's in every term, let's take n plus 1 common. Then we are left with this minus 1. So this becomes minus 1. This part goes off, so it's minus n and this. So can we do anything? No, we cannot. So let us just further see. This one has minus 2 and we can see one thing, minus 2 and minus 1, right? So minus 2 and minus 1, and if we take minus 1 common, we get 2n plus 1, which is also here. So we can take that common. So let's do this step over here. So we have minus 1 minus n 2n plus 1 minus 2n, and we can see that 2n, these two can be put together. So minus n 2n plus 1 minus, so these two added together, so this becomes 1 plus 2n, and then we take 1 plus 2n common, so 2n plus 1 common, and we have minus n and minus 1, and we take the minus 1 common, so this becomes positive. So that's what we have here. Okay, so again we take another n plus 1 common, so we get this n plus 1 square. And lastly we have this. We cannot do anything further, I'm assuming, so let us open the bracket. So we are opening the bracket, so this becomes n square plus 2n plus 1 minus 2n minus 1, 1 cuts off, 2n cuts off. So this is simply n square. So this part just becomes n square. So n square into n plus 1 square, and then we take the 4 to the right. So that's how we get the result. So it requires a little bit of exploration, this sum. All right, thank you. Hopefully you will have a good exam tomorrow.